Okay, in this presentation we're going to have a look at the gamma distribution. So an analyst is interested in using a gamma distribution with parameters alpha equals 2 and lambda equals 1 half. That is to say, with a probability density function of f of x equal to 1/4 times x times the exponential of minus 1 half of x. Okay, for x between 0 and infinity. Okay, so x is positive. State the mean and the standard deviation of the distribution and hence comment briefly on its shape. And then show that the cumulative distribution function is given by the following expression here. Capital F of x equals 1 minus, in brackets we have 1 minus a half of x times e to the minus x over 2, or minus 1 half of x. And again, for x between 0 and infinity, 0 otherwise for the probability density function, or the cumulative distribution function. I tell you what I'll do is start off with those, because what we'll be doing after that is talking about simulation a little bit. Okay, and we'll be looking at this curve here very shortly, but I'll just go to the main numerical parts there. So what we have here is a shape parameter and a rate parameter. So alpha is our shape parameter and lambda is our rate parameter. Now there's actually other ways of specifying the gamma distribution using different parameters, but in this case what we're using is the shape and the rate parameter. Now, just to cut a long story short, because this question is quite long, I just actually expressed the mean and the standard deviation in terms of alpha and lambda. So the mean, the expected value of x, is simply alpha over lambda, which is 2 over 1 half, which is 4. Okay, 2 divided by 1 half gives us 4. The variance would be alpha over lambda squared, okay, which is 2 over 1 half squared, which is 2 over a quarter, which is 8. The standard deviation is the square root of that, so essentially what we're getting is the square root of 8, which is 2.828. Okay, so that's straightforward enough, really. This is just knowing the shape and the rate parameter and knowing the mean and the variance and the standard deviation. Now, usually I probably will go into more detail in those, but this is quite a long video. Just to comment upon that, and this is actually part of A, as the claims are non-negative and the standard deviation is quite large relative to the mean, then the distribution is going to be quite positively skewed. Okay, so we can't get a negative value of the mean, so essentially the distribution is going to be positively skewed. It's sort of if you're fairly familiar with the idea of a gamma distribution and what a probability density function curve would look like, you probably just remark that it's positively skewed and why it would be positively skewed. Okay, that's just sort of follows on from the mean and standard deviation. That was really part B. So that was actually part A, not part of part B. Now, the second question is, show that the cumulative distribution function, capital F of x, is given as follows. So this really is the main part of our question. Okay, so the cumulative distribution function, capital F of x, is the integral of the probability density function. We'll include our limits there, x to from 0 to x as well. Okay, that should be in there. Now, so in this case, what we're going to do is express this in terms of, actually, we should really put it in like this. What we're going to do here, and I should not have put it in terms of f of x. What we'll do is put it in terms of a different variable, a dummy variable, and we usually use something else like t. Okay, so you don't have to really worry about what t is, because when we evaluate it as a definite integral with 0 and x, then it resolves itself into a function of x. So it's just temporarily we put in a different variable when we're integrating it, and then it resolves out when we evaluate it using the definite integrals, the upper and lower limit of integration there, 0 and x, and then what we want is a function in terms of x. So what we have here is 1/4 of the integral from 0 to x of t times e to the minus 1 half of t dt. Okay, so let's just check that. Go back up there. So it's essentially just replace x there with t, and that's exactly what we get. Integrated, we take the 1/4 out just for the save ourselves a bit of bother. But there, what we're going to do is get going at that. So this, I'm going to come back to the 1/4 later on, but essentially what I'm going to do is evaluate this part here. And what we're going to do is set that up as an integration by parts. Okay, so this is the integration by parts formula here. Okay, and what we're going to do is let u equal to t. That means du dt is equal to 1. That means du is equal to dt. dv is the exponential, is the e to the minus 1/2 of t dt. And when we integrate that, which is the integral of that expression there, we get minus 2 times the exponential of minus 1/2 of t. So I'll just actually make it a bit bigger there. Minus 2 times e to the minus 1/2 of t. Okay. Essentially what we do is divide by a half, but in this case, or minus a half, but in this case that becomes multiplying it by 2. Okay, the u and u dt was fairly straightforward. Now, just a bit of attention to detail is important here, but really this is fairly straightforward. And we will resolve it as much as we can, but we won't go any further than necessary. Now, in this instance, I'm just looking at u and v. I'm going to come back to the 1/4 there later on. So uv minus the integral of v du. Well, u is equal to t, and v is minus 2 times e to the minus 2t, minus a half of t, sorry, e to the minus 1/2 of t. Okay, so that's our uv expression there. And minus v du. Well, du in our case is dt, and v is minus 2 times the exponential of minus 1/2 of t. So essentially what I'm going to do is bring out the minus 2. So that's why I end up with this plus 2 here. Okay, and this is a fairly straightforward integration. So that is minus 2 times e to the minus 1/2 of t. So minus 2 times plus 2, we get minus 4 down here. Okay, so my pen is slipping there, but essentially what we end up with here is minus 2t minus 4 times e to the minus 1/2 of t. So I'll just pick it up from where I left off. I just have to pause it for a second. So we evaluate the integration by parts as minus 2t minus 4 times the exponential of minus 1/2 of t. So the integral overall actually is 1/4 of that. Okay, so I have to sort of factor in that 1/4. So that's where I go from minus 2t minus 4 to t minus t over 2 minus 1 times the exponential of minus 1/2 of t. And what I'm also going to do is evaluate it at the upper and lower limit of integration. Okay, so here we evaluate the expression at let t is equal to x. Here we evaluate the expression let t equal to 0. We simplify, and x, for the x expression there, and then just subtract one from the other. From the x expression there, essentially that just resolves itself to plus 1. Okay, so we end up with down here with this expression here, 1 minus x over 2 plus 1 times the exponential of 1/2 of x. And essentially that is what we're asked to do in the question there. That's exactly what we're asked for. I'll just do a quick edit in the video. I just realized that there is missing a plus sign there. So that actually should be 1 minus 1 plus 1/2 of x. Okay, so the derivation is right. It's just that the original question had a minus sign where it should have had a plus sign. Okay. The analyst wishes to simulate values x from this gamma distribution and is able to generate random numbers u from a uniform distribution on 0, 1. Specify an equation involving x and u, the solution of which will yield the simulated value of x. And comment briefly on how this equation might be solved. Okay, now if there was weightings for this question, it probably would not have much of a weighting. And if you think about that, it might put you only get 2 marks as opposed to 10 for the one we've just done. And if you think about that, why is that? Because you're actually not asked to solve it. You're actually state how it's solved. Okay, so we're not asked for a derivation there. Okay, we're asked to state one equation. Okay, and in this case, it's fairly straightforward. F of x is equal to u, or actually that should be f of lowercase x. Okay, which is, say, 1 minus a half of x over 2 plus 1 times e to the minus a half x equal to u. Okay, so this is the expression we would use to generate random observations of the gamma distribution. Okay, now what you might do is you start fiddling around with that, or trying to solve that, or resolve that expression in terms of u, just make it, or in terms of x, is that you might find life very difficult for yourself. And what you might also find is that that's actually not what you were asked. So essentially what it's sort of leading you towards here is that this really is a numerical solution was required using numerical estimation methods, numerical computation. And that a sort of a derivation like we've just done, is probably just too much to do. So basically, so it's not that it's impossible. I didn't really check, actually, to be honest with you, but essentially I know the way that this question is phrased. Let's go back up here. Is that it's directing you towards something else. It's not directing you towards a derivation like we've just done in part B. Okay, so that's it. The last question here is the graph below plots f of x against x. Use this graph to obtain the simulated value of x corresponding to a random number u equals 0.66. So this is straightforward enough. You don't really get so many of these anymore, okay? But it doesn't really come up on the page there. It's just essentially a big curve. I'll colour in a little bit of it here, particularly the bit I need. Okay. And what we do here is f of x. This is f of x here. So essentially, this is what we have as our u value. So u equals 0.66. Okay. 0.66, which is around here. Okay. Where it hits the line, we go down. So it's on that line here. And this hits just short of 5. What is that? So this is actually broken up into 10. So, oops. 1, 2, 3, 4. Okay. So it actually looks like it is 4.5. That if we have a value of u equals 0.66, that means that we should get an observation, a realization for the gamma distribution of 4.5 roughly. Okay, that's simply how it works. These are great little approaches for simulating random numbers. I love these. This is what a computer does, though, really, but so it's about 4.5. That makes sense. Okay, I'll just scroll up there a little bit. Okay, we'll leave it there.